From here, d alpha over f alpha equal to k dt. So that means 0 to alpha is equal to kt, and kt equal to your g alpha. So that means 0 to alpha d alpha over f alpha, this thing is your g alpha. So I can write g alpha here equal to this a over phi exponential to b. Can you take e over rt as a variable, say y equal to e over rt. Write down this integral in terms of y. Just do it. Take y equal to e over rt. Gopal, are you just looking at the board or you are doing on your notebook? If you have done, tell me the expression.
e to the power y by y square into 4.
E to the power minus what?
Minus e to the power y by y square into 4.
E to the power y into the minus y or y?
Sir. Actually, y minus 2.
In earlier batches, my experience from real degrees was better in one sense. Is the following, that this type of question when I used to ask, I used to get very quick answer. But this batch I am really impressed by the attendance, overall attendance and sincerity. But earlier batches I saw that very sharp quick answers. I remember one girl who went to applied materials later, Kasturi. She used to come like once in a while, like didn't used to come. I used to be very angry. But whenever I used to ask this type of question, like very quick answer I used to get. Why not when say
minus e by ry square into exponential minus
in terms of y? Are you getting this? This integral? So this integral we will say this integral let us write it as dy. Then our g alpha is equal to a e over r exponential integral, so this integral py integral, this integral is called exponential integral or temperature integral, or sometimes it's called Arrhenius integral. This has no exact solution. So numerical or approximate solutions are required. So people have tried to have series expansion of Py, different series expansion, couple of different solutions and with assumptions. I will just write down for our class. One is Coates and Redfern. They said that this integral 0 to t exponential minus e over RT or I can just in terms of py indefinitely. So one was Coates and Redfern, their approximation about Py, and they got this approximation because some other people have been able to write Py in our expansion of series expansion. So there are two, three different forms of series expansion. They chose one, and they chose the asymptotic series expansion, and they took the first two terms of the series expansion, and they come up with this Py approximation is this. Another approximation was given by Doyle, and they noticed that if log Py is plotted against y, log Py varies linearly, and what they found out that log of Py in a now what is y? Y is e over RT. Usually for our case, like for any of the transformation, phase transformation we talk about, e over RT lies in the range of 15 to 16. So in this range, in the range where they have found that log of Py varies linearly with y, and that linear expression they found out to be this. There are other assumptions of this exponential integral, but let us, for our class, for those 6 models we will discuss, these assumptions we will take. Either for some models we will use this Py expression as that, or for some model we will use log py expression as this. Because we need py, because our g alpha is nothing but ae over phi r multiplied by py. And py is nothing but this one, this temperature integral. The first method we will discuss about, the first method was direct differential method. Direct differential. So through this method we can write this d alpha dt equal to a over phi exponential minus e over rt f alpha. So this equation you know. D alpha dt. How come this? This phi d alpha dt. So phi d alpha dt is nothing but d alpha dt, that is the rate. So d alpha dt multiplied by phi is, this is k multiplied by f alpha. That is direct equation. So this equation comes from this equation, that d alpha dt equal to k f alpha, which is giving this one, because k equal to a exponential minus e over rt, and your d alpha dt equal to phi d alpha dt, and phi is the heating rate. Fine with this. Phi is nothing but dt dt. So from here we can just take d alpha dt over f alpha equal to ln of a over phi minus e over rt. Just rearranging this equation and taking ln, we can write this. Now what you do, you plot ln of this versus 1 over temperature. The slope will give you, plot this versus this 1 over temperature. The slope will give you activation energy E, and your intercept will give you A. How can you plot these? So at different temperature, for example, we drew this, no? This is the diametric curve we think of. So at different temperature I can find out alpha. So different temperature, alpha values we can find out.
Alpha versus T.
And so we can plot alpha versus T. So we can find out d alpha dt also at different temperatures from that plot, from the slope of that plot, alpha versus T plot. And at that point of alpha, what will be, if you know the function f alpha beforehand, then you can get a value here. So for a particular temperature, you can get a value here, ln of that. For that temperature, you repeat for different temperature, you can find out for all these values. So you can find out f alpha, because you know alpha, you know f alpha, then you can find out ln of d alpha dt was divided by f alpha. You can find out 1 over temperature. So you can get this, you can plot this versus this, and you should find it as a straight line whose slope will give you activation energy and intercept will give you A. If you do not find it to be straight line, you use some other expression of f alpha, you vary the f alpha and see which f alpha expression gives you the best straight line, from whose slope you can get the activation energy. So it's a model fitting type of model. There is the second model fitting type of model, which is Coates and Redfern model. Which says G alpha equal to, our main equation was this, AE over phi r, then Py. So they use that Coates and Redfern approximation for Py. So it is AE over phi r, then e to the power minus y over y square, 1 minus 2 over y. So you put the value of y, you will get AE over phi r e to the power minus e over rt over e square over rt square, one minus 2 over e over rt. That is your G alpha. I am erasing this. Have you noted down this dual approximation for log Py? Minus 2.315 minus 0.4567 y. Just take G alpha by T square will be equal, just take T square here and take logarithmic of that. Then you will have ln AR over phi E multiplied by 1 minus 2 RTE over E minus E over RT. So you are getting this type of expression for if your E is very high, you can ignore this with respect to 1. If you do not want to ignore, you just use a average temperature of the temperature range through which the transformation is happening. Then then this is a constant term which is not varying with temperature. Either you can ignore this because most of the cases for us E is high enough. So this fraction can be ignored with respect to 1. Otherwise, if you do not want to ignore, use a particular average temperature in that temperature range. So then if you plot ln g alpha over t square versus 1 over temperature, it will give you, its slope will give you the activation energy. But you need to know the expression for G alpha. It should be a straight line, but if it is not a straight line, change the expression of G alpha, find out which particular model fits the curve so that it fits to a linear curve, gives the best linear fit. That will be your G alpha. Then you can find out from the slope E and from the intercept A. These model fitting models, type of models, you need to know the model's prior value. You need to know the model expression. Then only you can find out. But you can, through this you can find out E and A both. Now we will end the class with one of the model free models, which is Kissinger model. So it's a model free model, that means you can calculate the activation energy without any modelistic model approximation or model expression. Actual expression you do not need to know. But there Kissinger proposed a kinetic analysis method for reaction order models, that is, they said that F alpha usually varies like this. 1 alpha to n, that is nth order reaction, action and transform to the power n. Rate depends on. So F alpha expression most of the time. So they use this one to start with. So your d alpha dt is equal to k f alpha. K is a exponential minus e over rt. 1 minus alpha to the power n. So can you find out at what, for what condition the reaction rate will be maximum? Double derivative of this means another derivative, ddt of this equal to 0. You can you make it on your own notebook? Just take a derivative with respect to time again. So ddt of this, which is ddt of the whole thing, and make it 0. this much is nothing but d alpha dt is this one. So this is your d alpha dt. So after that step, we can write this is phi. So if you make it 0, your reaction rate will be maximum or say Tm is that temperature where reaction rate is maximum should be equal to so if you take ln at both sides, ln of phi over t tm square ln of what I want to say, if you note this, what you are getting, that if you plot ln phi over tm square versus 1 over tm, it will be a straight line. What is this tm? This is your, in a DTA experiment or DSC experiment, this peak. So what you do, and for different phi values, for different heating rate, use different heating rate and find out where the Tm is. Say phi 1, Tm1, phi 2, Tm2. Like this you find out. So you know the phi values because you are heating at different rate. Find out Tm. So phi over Tm squared, take ln and plot it against 1 over Tm. to know the peak temperature. You can, from that, the slope will, from the slope you will get the activation energy. So this is the Kissinger method of finding the activation energy. So ultimately when you are using this, you do not need to know the form of F alpha. Although they started with F alpha of certain form for their derivation in their paper, but ultimately you do not need. You just need to heat it at different rate and find out the peak temperature for different heating rate or cooling rate. And you plot ln phi over Tm square versus 1 over Tm. Tm is that temperature, peak temperature. We are assuming the peak temperature is the temperature correspond to the maximum rate. That's which we got by equating this expression to be equal to 0. Somebody, can you give me please 5 minutes? I have to do attendance. Okay, thank you.